Good morning, Seeders. In this video, we have an absolute beauty of a question for you. And as we're working through it, I would like you to take note that it doesn't just cover one topic. So you can see in this first question, we've got a question about wavelength of radio waves linking to the waves topic. Then we have a question about distance time graphs that is linked. And finally, we have a question that requires us to use the SUVAT equations. So this is one single question on an exam paper, but it really jumps around in terms of the topics that it covers, and this is not unusual. I would also say that this is very much a higher level question. So here we go. Let's get stuck in. The image below shows a student playing with a remote controlled car. Okay. The remote control transmits radio waves to the car aerial. The transmitted radio waves have a frequency of 320 megahertz. The speed of radio waves is 3 times 10 to the power 8 meters per second. And we are asked to calculate the wavelength of the radio waves and give the unit of wavelength. So clearly, this is a job for CEMU. And the first thing we're going to address is this 320 megahertz up the top. So 320 megahertz needs to be converted to hertz, and mega means million, so it would come to 3.2 times 10 to the power 8 hertz. Then we recall our equation for wave speed, where the velocity of the wave is equal to frequency times wavelength. We are going to substitute in our numbers. So we have been given the velocity of the wave as 3 times 10 to the 8 is equal to, we've got the frequency of wave, which is 3.2, also times 10 to the 8, note, multiplied by wavelength. Always substitute in the numbers first. Now we do our rearranging. So this would rearrange to 3.0 times 10 to the 8 divided by 3.2 times 10 to the 8. And actually it's quite nice that they are both to the same power, because really you can ignore the 10 to the 8 when you do your final calculation, is equal to wavelength. So this comes to 0.9375. We haven't got recurring decimal places and it doesn't specify how many significant figures. So I would suggest that we just need to go with the 9375 in the answer. And of course the unit for wavelength is meters. You can see that this question is a whopping 5 marks, and that will be because we've got this conversion that we have to worry about at the start, and then we are rearranging the equation. Okay, next up. In part 2 of this question, we are given a distance time graph for the remote control car. So we have described the motion of the car during the first 30 seconds. You can see that the line is curved. So this means that the car is getting faster or accelerating. So remember, a curved line on a distance time graph means that the speed of the vehicle or object or whatever it is changing. Next, determine the speed of the car 20 seconds after it started to move. Okay, so we want to know the speed of the car at this point here. So I'm going to get a pencil. And this is a case of drawing a tangent to the curve. So the way I would do this is I would put my pencil on the line at the 20-second point, then I'll bring my ruler to the pencil. And we want to draw a tangent where the line is just kissing the curve. What I'd then recommend is you make your line really quite long. There we go. So there's my tangent. And I'm taking it from, let's go, look, from 10 seconds to 30 seconds. So I've got a time here of 20 seconds, which I'm just going to note there for when I get to the calculation. We can then have a look to see if the remote control car had been travelling at this speed the whole time, we can see how far it would have gone. So from 0 meters up to, so this would be 5 meters. So here would be 5.6 meters. So again, I'll just make a note of that. We've got 5.6 meters. All right. We've now got all of the information that we need from the tangent, so back to CEMU. We don't need to do any conversions because we're working in meters and seconds, that's fine. We are going to use V is equal to distance divided by time. We are going to substitute in our numbers. So we have velocity is equal to the distance, which was 5.6 meters, divided by the time taken, which would be 20 seconds. And we can simplify that expression. So I've got 5.6, and that comes out to 0.28 units. So remember our units are meters per second. Now, as it happens in this particular question, the units are given, but it's still good practice to write them anyway, I would suggest. Always get in the habits of doing things properly. Again, a whopping 4 marks for this one, even though it's one of the simpler equations, because of course we had to do the work with the tangent first. Okay, fine. This brings us to the final part of the question. So we've got a different car now, accelerating from 0.12 meters per second to 0.52 meters per second. The acceleration of the car was 0.4 meters per second squared. The work done to accelerate the car was 0.48 joules. Calculate the resultant force needed to accelerate the car. Now this last 2 bits, so we've got work done given and force, which puts me in mind of the equation work done is equal to force times distance. But the problem is, although we've been given the work done, we've not been given the distance, but we have got an initial velocity, a final velocity, and an acceleration, which puts me in mind of the SUVAT equations. So I reckon we could use v squared, final velocity, subtract u squared, initial velocity, is equal to 2, multiplied by acceleration, there's our acceleration, multiplied by distance. So with the information given, we can use v squared subtract u squared equals 2as to find the distance. And then once we've got the distance, we can use the work done on the distance to calculate the force required. Okay, let's get cracking. So all units given are absolutely fine. I've got meters per second and meters per second squared, so I don't need to do any conversions. Lovely. My equation, as we've already alluded to, or the equation we're going to use for the first half of the question is v squared subtract u squared equals 2as. I'm then going to start substituting in my numbers. So I've got final velocity of 0.52 squared, subtract an initial velocity of 0.12 squared equals 2 multiplied by 0.04 multiplied by the distance, which is what we're trying to find out. I think the first thing that we'll do is we'll just simplify some of these numbers before we start rearranging. So I've got 0.52 squared, which is 0.2704 subtract 0.12 squared, which is 0.0144. And I think we can simplify as 2 times 0.04 as well. So that gives us 0.08 multiplied by S. Let's do a bit of rearranging now. Actually, we could do two things in the next stage, actually, couldn't we? So let's do the 0.2704 subtract 0.0144, which gives us 0.256 divided by 0.08. You can see I've put the 0.08 over now, is equal to the distance. So we simplify that expression, and that tells us that the car has moved 3.2 meters. Now we've got everything we need for work done is equal to force times distance. So we go again, no conversion in all my right units, all my SI units. My equation is work done equals force times distance. I'll plug in my numbers. My work done, remember, was 0.48 joules. We don't know the force, we're calculating that, but we do know the distance now. So now I'm going to rearrange. So I've got 0.48 divided by 3.2 is equal to the resultant force. And that comes to 0.15. That's the final part of our calculation, so we're going to make sure we remember the units. Oh, I've gone off the bottom of the page, sorry. Giving us 0.15 newtons. Epic. And that was just one question where we had 3 calculations worth 5, 9, 15 marks. There is a link to the question in the description below. I hope the video was useful. If it was, don't forget to subscribe. This is Mr. Rolf signing off.